Okay, so a little bit of a calculus conversation here. I haven't done this type of explanation before quite this way, so on the fly, let's hope I do justice to the cause. We'll find out. My screen is a little dirty. All right, so students in calculus encounter integrals, and almost every class I've ever taught, some student asks, what happens to the dx? The integral of 3x squared dx from 2 to 3 is really all about the change of the cubic function from 2 to 3, which is 27 units minus 8, 19 units. And what happens here? What's this all about? Well, I think I could ask the question, Paul, pose a question to you. 3 times 5 is 15. Well, where'd that 5 go? Length times width equals area. Where'd that width go? Rate times time equals distance. Where'd the time go? Well, you could be my age, you ask that question a lot. And I think this is actually a product. dx is more of a concept than an actual number. And it's really a small difference in x. An x2 minus an x1. It's a concept. But we can approximate it and see how numbers work. And that's what I'm going to do here. I'm going to crunch some numbers, look at the geometry of what's going on, and hopefully you get a little entry feel for two things. One, instantaneous rate of change and average rate of change. So if I had a quadratic and I went from one point to another, from this place to this place, that's called displacement. It's a whole joke. Then that's what is referred to as an average rate of change. It's a pretty big jump from this x to that x. But if I went from, let's say, 2 gets me 4 units squared. If I went from 2.0001, those 4 digits, very small change from this number to that number. It turns out I get 4.1234, 1234. You're checking out a calculator. That's what you get. And so we're going to look at some of the patterns that emanate from this calculation. And let's start with average rate of change. 3 gets me 9. 10 gets me 100. What's the average rate of change? x2 minus x1. y2 minus y1, that's how we compute change. Well, 100 minus 9 divided by 10 minus 3 actually is 13. So why don't we just talk about the rate? 13 to 1. Let's do 9. Okay, I can leave this. I can leave this over here. 9, 81. 9, well, that actually comes out to be 12 to 1. So 81 gets me 12 to 1. And if I do 8, I get 64 minus 9, which is actually 55, just to show it. And I get 8 minus 3 is 5. Yeah, boy, you got 11 to 1. I wonder what rate I'd be changing at if I went to 7. I think it would be 10 to 1. And 6. I think 6 would be 9 to 1. And 5, I think, would be 8 to 1. And 4, I think 4 would be 7 to 1. And I think at 3, it's going to be 6 to 1. Well, let's get a small change in x going. Let's get a small change in x and see what it is. 3 point, I'll do 5 decimal places. That's going to be even more accurate. That gets me 9.1234.5. Oops, I need more space. 1, 2, 3, 4, 5. Boy, I changed by 0.001. Yeah, the 9s didn't change, did they? No. But if I divide this by 0.00001, I get rid of that really tiny amount, I got a 6-to-1 ratio. Now, what I was doing here when I started at 10, it was really to get an intuitive feel for what a limit is. Because I could push these decimal places out as far as I want. And every time I push another decimal out, 3 more decimal places, I think I did three more, I get more accuracy. And so I think when 3 is being squared, the table values are going up at 6-to-1, kind of showed it. So let's go back to this x cubed function, my favorite function, x cubed. It sure looks like, if I look at these rates again, so let's look at these rates one time. So the rate at 3 was 6, the rate at 4 was 8, the rate at 5 is 10. I think there's a pattern there. I think the rate at which a quadratic change is 2x. Yeah, and I know what x is on a quadratic. X is the side length. And I know what an x over here is in a square because the side lengths are the same. And dx is actually when I move that dimension up just a little bit, a little difference in x, something like 0.01 that I tack on to 3. Then I get an x dx, little strip of area, and another one over here, and a little bit of error there. But that is a change dimension. If this is 3, then I'm saying I'm moving over 0.01. I don't forget, but I'm just saying it's a small change in x. Then the area accumulation comes from 3, because this was a 3 by 3, and that could have been some other number. Okay, and we can see how the area of a square changes. Okay, now the question is, how does a volume, what's going on with volume? And then we'll get back to 3x squared dx eventually. Okay, so if you cube 0, you get 0, and if you cube 3 decimal places, you get 9. Okay, not much change. Well, if there's no box there, I guess a little change in dimensions, and you're not going to get much volume change. If you had a 1 by 1 box, 1 times 1 times 1 is 1. And 1.001 is 1.0303001. I can see the rate of change there is 3-to-1. And 2.001, 3 decimal places, 9 decimal places, 0.012006001. And if I divide 0.001 into I think I'm changing at 12-to-1. I think that's the rate at which I'm changing, 12-to-1. And 3 gets me 27-to-1. Wow. Wow, I wonder if I could come up with a, 3x squared. Oh, geez, 3x squared seems to be matching up with this. 0, it's not changing. It's changing at 3-to-1. It's changing at 12. There seems to be some matching up here with the rate at which this function is changing, 3x squared. And I've done this before, this high-tech explanation. You know, I'm bringing in high technology here. This is a volume of a box. Let's say it's a 2 by 2 by 2. And I just change the dimension of the box. I'm going to put a layer of volume on top of volume, which means that this length might be, 2 by 2 by 2. 2 by 2 by 2 is this one. This one might be 2.01 for a height and 2.01 for a width. And I guess if I square that, it's pretty close to squaring 2, right? 2 squared 4. And how many of these shapes do I have? It looks like I have a square. Looks like I have 3 of them. Okay, but this got volume, so where's that third dimension? It's the thickness of the cardboard. And I'm saying you want to get an intuitive feel for just how thin this is, because the thinner it is, the more accurate the calculation on how this volume is changing. And can you see that thickness is 0.01? So there's a relationship here. So what is 3x squared dx? Let's put a dx here. Well, I'm using 0.001 as my difference in x. And what is 0.001 times 12.0? Whoa, I got to move this decimal 3 places to the left if I divide by 0.001. And that's going to get me 0.012. If I divide 12.012 by 0.001, I'm moving the decimal over 3 places, and I get that. Well, let's go back to the cubic. Oh, 2.0. Oh, it has jumped by 0.012. There's the change. So it looks like 3x squared dx is adding up these changes. Now, what I should have had here was 2.002 gets me 8 point, I don't know that pattern. I should have had that done, because what happens when I add 0.012, I got that number basically giving this amount. And then I would get a new amount here, but it's a slightly bigger dimension, slightly bigger number than that is going to get added on to that. And I'll know the location of 2.002 cubed. And that's what this symbol is. That's adding up all these changes. And I could have gotten that change by looking at 3x squared dx. And so it's the same thing as a youngster, you know, who's 3 feet, and a year later he's 4 feet tall. All right. But if you broke it up into daily increments, well, how much did he grow, or she grow, or they grow, or whatever, from day 0 to day 1, there's a little bit of growth that can be measured. And if you keep adding up all of those measurements, you have to know the rate at which the person's growing, right? Because rate over time gives us a change in amount. Okay, so we could look at it a little graphically. All right, from a graphical standpoint, here's 3x squared. Right, so what's dx? Dx is the change from 2 to 2.001 in our example. That's really a Riemann sum. But we gain more accuracy as we push out the zeros, and that's the notion of a limit, right? Which kind of says we know what the rate is at that instant. Okay, this is a kind of a one-sided approach. All right, so to get an accurate area, this is a rate, the rate at which x cubed is changing, so that's a rate. You can think of dx as time, and so we get a little increment of change for the x cubed function because we just saw it happen in those tables. And so therefore, if I went all the way over from 2 to 3, then as I build in accuracy, I'm going to get 19 units of change here. 19 units of change. In fact, we said that the square changes according to 2x, right? So x squared, the derivative of x squared is 2x, right? Well, if I cut that in half, I get x, which means I'm cutting that in half. So let's look at that accumulation and very quickly, and maybe you'll get a visual representation of accumulation of change. Let's just do 2x, the heck with it. Okay, so here's y equals 2x, and let's go to some places. Let's start from 0, and let's start building in those 2x dx models. So this is dx 0.001 times 2x, and let's actually do some numbers. All right, let's go from 0 to 1. At 1, my height of my curve is 2 times that, 2. So what's the area of that triangle? 1 times 2 cut in half. So as I move from 0, there's no area, right? There's no area, but as I draw an area and I get to 1, my area of that triangle is 1. Let's go over to 2. Well, 2 doubled is 4. So what's the area of that triangle? 2 times 4, right? With the 2 times 4, 8 cut in half. Oh, gets me 4 units of area. Let's go to 3. Double is 6. So what's the area of that rectangle? 18 divided by 2, 9. Anybody want to guess what 4 is? If you're looking for patterns, if you said 16, you'd be right. So what is the accumulation from 0 to 4 given this rate function and all of these widths? All of these height times widths, it's giving me an area statement of x squared from 0 to 4. And now you're doing the fundamental theorem. Okay, I like to introduce that day 1 of a calc class so that we can begin to have longer conversations and derivatives and just have at it. Okay, so I'm rambling a little bit and a little awkward explanation because I've done it before. And repetition's my friend. So next time I explain this to a class, I hope I do a little better job. All right, but maybe there's some things there to think about. So ponder. All right.